Now let us perform an experiment. Here you can see two protons, precessing around the z-axis. I hope that you can recall that the z-axis indicates the direction of a magnetic field line. Instead of only these two protons, in reality there may be 8 pointing up and 6 pointing down, or 82 up and 80 down. There should only be 2 more protons pointing up. As we know, these are the ones that have a net magnetic effect, because their effects are not cancelled out. Now let us send in an RF pulse, which has just the correct strength and duration, so that one of the 2 protons picks up energy to go into a higher state of energy. In other words, points down, walks on its hands. The longitudinal magnetization, up to now resulting from 2 protons pointing up, will decrease. In our example, to 0. 1 pointing up is neutralized by 1 pointing down. But, as both protons are in phase, there is a new transversal magnetization which had not been there before. Try to imagine tilting a longitudinal magnetic vector 90 degrees to the side. Let's repeat that. The RF pulse tilts the longitudinal magnetic vector 90 degrees to the side. Such an RF pulse is called a 90-degree pulse. Naturally, other RF pulses are also possible and are named accordingly. For example, 180-degree pulse. To really understand this, let us look at another example. Here we have 6 protons pointing up. We send in an RF pulse, which lifts 3 of them onto a higher energy level. The result? We no longer have a longitudinal, but a transversal magnetization, again having used a 90-degree pulse. What happens when the RF pulse is switched off? 2 things happen. Protons go back to their lower state of energy, and they lose phase coherence. It's important to note that both processes occur simultaneously and independently. For the sake of simplicity, let us look at what happens step by step, and first focus on the longitudinal magnetization. After the RF pulse is switched off, 1 proton goes back to the lower energy state, resulting in 4 protons pointing up and 2 pointing down. The net effect? We now have a longitudinal magnetization of 2. Then the next proton goes back up. Now 5 protons are pointing up, and 1 down, resulting in a net longitudinal magnetization of 4. After the next proton goes up, longitudinal magnetization equals 6. You have surely already noticed that the transversal magnetization decreases at the same time. Why is that? You should be able to answer this. After the RF pulse is switched off, the precessing protons lose phase coherence. Let us now leave out the little red arrows, each of them representing a single proton, and focus on the sum vector. When the RF pulse is sent in, the longitudinal magnetic vector is tilted 90 degrees to the side. As we already know, this vector moves corresponding to the precessing protons, but for the sake of simplicity, we'll leave out the motion. After the RF pulse is switched off, the transversal vector decreases, while the longitudinal vector increases. As you remember, vectors represent forces of a certain size and a certain direction. If you add up vectors pointing to different directions, you will come up with a direction that is somewhere in between, depending on the amount of force in the original directions. If we do the same with the longitudinal and the transversal vector, we get the sum vector. This sum vector is very important, as it represents the total magnetic moment of a tissue in general, and thus can be used instead of the two single vectors, representing longitudinal and transversal magnetization separately. Our magnetic sum vector, during relaxation, goes back to a longitudinal direction, in the end equaling the longitudinal magnetization. What we have to remember is that this whole system is actually precessing, including the sum magnetic vector. And thus, after the RF pulse is switched off, the sum vector will actually perform a spiraling motion. I hope that you recall that a changing magnetic force, moment, can induce an electric current, which is the signal that we receive and use in MR. So if we put up an antenna somewhere in our last example, we will get a signal like this one. This is easy to imagine if you think of the antenna as a microphone, and the sum magnetic vector as having some kind of a sound-emitting device like a steam pipe at its tip. The further the vector goes away from the microphone, the less loud the sound. The frequency of the sound, however, remains the same, because the sum vector spins with the precessing frequency. So the signal from our experiment disappears with time, however, has a constant frequency. This type of signal is called a free induction decay signal, or FID signal. By now, it should be obvious that the magnetic vectors directly determine the MRI signal and signal intensity by inducing electric currents in the antenna. Instead of the terms longitudinal or transversal magnetization, we can also use the term signal or signal intensity at the axis of our T1 and T2 curves.